Okay, this is 2009, question 5. It's interesting. I usually put that up here. All right, 5A. Answer the following questions using the information related to reactions X, Y, and Z in the table above. For reaction X, write the expression for the equilibrium constant, not Kc, but Kp. And so remember, Kp uses gas pressures. And so the first thing about this problem, and they will do this to you all the time, is that you have to remember that solids and pure liquids, the reason why I say pure liquids is that aqueous solutions are also liquids, like when you dissolve sodium chloride into water or an acid into water, but they're not a pure liquid because there's a solute dissolved in a solvent. And so what happens on this one is that, um, let me move this down a little bit. I hate when I have to put the pen so far up there, so far down on my tablet. So KP is, remember it's right over left. This is what the AP board does. I generally don't do this, but this is an AP question. So the first reactant, and by the way, KP only, pressures only affect to gases. We never talk about the pressure of a solid or liquid. We sometimes talk about the vapor pressure of a liquid, but then that's the gas pressure over the liquid as it evaporates in a closed container. And so it's P for pressure. The first product is CO, and then we're going to close it. And because there's a 1 here, there's no power. If you want to write down the 1, you can, but I think it's kind of redundant, times the pressure of the hydrogen gas. And again, um, there's an implied 1 here, so you can also put the implied 1 there. Carbon is a solid, it's not in there, and then it's the pressure of the water vapor. And again, that's a 1. And so that's a pretty easy question. Going to the next slide, B, for reaction X, will the equilibrium constant Kp increase, decrease, or remain the same if the temperature rises above 298? Justify your answer. Okay, kids really struggle with thermal. I love thermal, but kids struggle with thermal. Here's what you got to know about reaction X. Because they gave you the fact that the enthalpy or delta H was positive, that means it's an endothermic reaction. So first of all, when we go here and we have this reaction X, which is CS plus H2O gas, goes to um, CO gas plus H2 gas. They told you that delta H was positive. The number doesn't really matter. It's 131 kilojoules per mole. But it's positive, which means it's endothermic, which means, remember now, endo sounds like into. Another way of thinking of this is that you have to put heat into the reaction. Heat is a reactant, not a product. So exothermic heat is produced, and so heat is a product. Endothermic heat is needed to go into the reaction to get it to go. So it's a reactant. Now the question is, and this is the Le Chatelier's principle. They love Le Chatelier's principle. If the temperature increases, what that means is the stress that you applied to equilibrium is you made the reaction vessel, whatever, if it's in a beaker or a flask or some kind of cylinder on a piston, I don't know. But the flask is that you made it hotter. You increase the temperature. Remember, Le Chatelier's principle says when a reversible system is at equilibrium and a stress is introduced, it will shift in such a way as to relieve the stress. And so when it gets hotter, it doesn't like that it's hotter. It switches to the side that's cooler. This means the equilibrium um, will shift to the right. And when the equilibrium shifts to the right, it means, now remember, Kp is the stuff on the right. You could see on the previous slide. Okay, so when it shifts to the right, you end up with more stuff on the right, and So more gas pressure on the right and less gas pressure on the left. Well, you have a bigger number in the numerator and a smaller number in the denominator, and both of these cause the equilibrium constant to increase or get bigger because the number in the numerator gets bigger, and then you're dividing by a smaller number, which also makes the answer bigger. And so the question is, that means that the equilibrium constant would increase. Justify your answer. This is, because you get a 50-50 shot of saying increase, decrease, but temperature goes up, this means the equilibrium will shift to the right. And if the equilibrium shifts to the right, KP increases. I did that to explain it to you. You would not have to do that on the AP exam. That would be enough. For reaction Y at 298, is the value of KP greater than 1, less than 1, or equal to 1? Now, this is interesting because if we go back and look at reaction Y, they gave you delta H, delta S, and delta G, and they're asking about K. And so the first thing you gotta know, this is one of those questions where it really helps to look at your review sheet, but you have a reaction, or sorry, not your review sheet, your formula sheet. And I always say this to you, girls are not real tough when they're having kids naturally. And the reason why I do this is there is a relationship between delta G and K for equilibrium. This is the equation that connects the thermo stuff, because thermodynamics is all about H and G and S, and K, which is equilibrium. And so the question is, and you got to remember on the old test, on questions 4, 5, and 6, you didn't get a calculator. So this is a question that you don't need a calculator to answer, and here's why. Although, I don't know that that would ever happen. If you look at reaction Y, you will see that delta G for reaction Y is a positive 29 kilojoules per mole. So let's think about this. This is positive 29 kilojoules per mole. And then R is always 8.314 joules per mole K. That's the value of R you use for thermal. T is 298 K. And this is in kilojoules, this is in joules. So really this probably better way is 29,000 joules. And then ln K, and the question is, what would K have to be? Less than 1, greater than 1, less than 1, or equal to 1 to make the answer positive? Well, think about this. This is negative. Temperature is always positive because the coldest temperature in the universe is 0, absolute 0. And so this would have to be negative. So first thing you got to get is ln of K has to be less than 0. Why? Because a negative times a negative gives you a positive. It has to be negative. Now, what kind of numbers, when you take the log, I don't care what the base is, are negative? Well, they're numbers that are less than 1. You guys have really struggled a lot with exponents, but let's just do log base 10. I know this is log base E, but the log base 10 of 100 is 2. Why? Because 10 squared is 100. And the log base 10 of 1,000,000 is 6. Why? Because 10 to the 6th is 1,000,000. But now an interesting thing happens is that the log base 10 of 1 is 0. Why? Because 10 to the 0 is 1. And now I'm going to pick a number less than 1. So the log base 10 of 1/10, which is 0.1, this is a number between 0 and 1, is actually negative 1. Why? Because 10 to the negative 1 equals 0.1. And so one of the things you have to know is that when K is less than when K is less than 1 but greater than 0, the logs, I don't care what the base is, it can be base E, base 10, is negative. And so, long story short, the answer to this question is, I'm going to hit extend page. The ln of K, something on the order of the ln of K would need to be negative, to get a delta G naught value that is positive. So K would need to be less than 1. All right, cool. That's kind of a tough question. On the basis of the data in the table, can it be predicted that Y will occur more rapidly than X? No. Delta G just tells you if the reaction will happen spontaneously. New terminology, thermodynamically favored. I like spontaneously because it means it happens by itself. Or non-spontaneously. Remember, spontaneous reactions, delta G is less than 0 or negative. Or non-spontaneously, which means delta G naught is greater than 0. Delta G naught just tells you if the reaction will happen spontaneously or non-spontaneously. It does not tell you, us, whatever, anything about speed. Nothing about speed. It could happen in a nanosecond. It could take 5,000 years. It just tells you if it will happen on its own or if you have to put some energy into it. But it doesn't tell you anything about speed. The branch of chemistry that deals with rate or speed is kinetics, which is the chapter I usually do right before this. And so kinetics is the branch of chemistry that deals with rates or speeds of reaction. All right, next slide, coming over here. Is S for the reaction positive, negative, or 0? So this is Z. If you look at your chart, you don't know anything about Z. And here's the thing. If delta S, so if the change in S, sorry, I don't think this has to be a change. If delta S is positive, remember that the definition of entropy is disorder. Delta S is positive means the reaction is getting more disordered. And if delta S is negative, it means it's getting less disordered because the definition of S is disorder. A negative and a negative is a positive. This is a fancy way of saying more ordered. And remember, we talked about that this second law of thermodynamics is that in spontaneous reactions, delta S of the universe is increasing. And what happens is if you throw a deck of cards off a cliff, they're not going to land all 52 right on top of each other in a perfect little pile because things go from order to disorder spontaneously. So we have to go back, and it'll be very obvious because if you look at this, and remember liquids and pure solids, 2 moles of gas is turning into 1 mole of gas. This is becoming more ordered. 2 moles of gas takes up more space than 1 mole of gas. And so delta S would be negative because it's getting less disordered. And so when we go back to this problem, they used to love this question. Is delta S for the reaction positive, negative, or 0? Justify your answer. I think there's, and so what happens is S is negative because this is what justify your answer is. 2 moles of gas in the reactants. I'm not so good writing with this. And 1 mole of gas in the products. So it is getting less disordered. Less disordered means negative. All right, we'll determine the value of delta H. I think this is the last one. Yeah, this is, I'm going to hit extend. This is Hess's law, and so I'm going to go back to the first page because it really helps. You guys will have it in front of you, but okay, I need to hit extend page. I don't need to look at this. All right, so I'm going to go back to the beginning. And here's the deal. I'm going to grab this eraser so that none of this stuff is junking us up so we can see what's going on here. All right, so when they ask you for delta S on the exam and they're giving you information, we have to do something with X and Y to get Z, because remember Hess's law says that you can add reactions together and add their delta H's and get the correct reaction. Now, the thing that's interesting when we do this is we need to have 2 COs on the left. And we are not going to use the CO right away, because what I want you to see is this reaction has a CO in it, and this reaction has a CO in it, or carbon monoxide if you prefer. And I always tell you, if you have a reactant or a product that's in more than one equation, shy away from it. Just let it come along for the ride, so to speak. All right, so I'm going to leave this alone for now. Hopefully it'll all come out in the wash. I need a carbon solid on the right. This equation has carbon in it. This equation does not have carbon in it. So I'm going to take this first equation and flip it, because that gets the carbon into the right position. So I'm going to go 2 slides over. No, I'm not. I'm going to go to the very last slide. I did extend, and I'm working off my worksheet right now. Probably should switch colors so that this makes sense to you. So I'm going to take that first reaction, which is reaction X, and I'm going to go, okay, I'm flipping it. CO gas plus H2 gas goes to Cs. Now remember this, in reaction Z, carbon solids on the right, and it has a 1 in front of it. And so I'm going to take the first reaction and flip it, because if I do that, it puts the C in the right position. But because I flipped it, delta H is negative 131 kilojoules per mole. And now this is in the right position. Now, when you look at reaction Z, I need CO2 to be on the right. And the first reaction doesn't have CO2 in it, reaction X, and I've already used it, so I can't use it again. Reaction Y has CO2 in it, but it's on the left, and I need it on the right, because reaction Z has CO2 on the right. So I'm going to take reaction Y and flip it, and so I get CO gas plus H2O gas goes to CO2 gas. And this is critical, because I need this. If you look at reaction Z, it has this and this on the right, plus H2 gas. And again, because I flipped it, delta H has to be negative 41 kilojoules per mole. And something beautiful happens when I add these together, because this cancels with this, and this cancels with this. And 1 CO and 1 CO gives you 2 CO. And reaction, sorry, that's really bad. And so what we have is 2 CO, carbon monoxide gas, and that's what we wanted. Everything else cancels. And then we have CS and CO2, and that is what reaction Z looks like. And so we have to add these together. 1 and 1 is 2. 3 and 4 is 7. So this ends up being, delta H ends up being negative 172 kilojoules per mole. And that is the answer to the problem.